Hey, folks. See, I wanted to do something a little different than my traditional, hey, everybody. I just wanted to spend some time with you today talking about colligative properties, and the colligative property of choice today is going to be osmotic pressure. And we have to kind of remember what osmosis is, going back to maybe our high school biology days or whatever. And so the idea is if you have something, you get to see the sample problem. If you have like a cell, that's the best I can do for a cell. Okay, and inside the cell there's molecules of maybe sugar. What's going to happen is there's going to be a flow of water into the cell to try to even out the concentration inside the cell and outside the cell. Okay, so that flow of a liquid to even out the concentration, which now you can probably see is a chemistry thing, but so that flow is a colligative property. Okay, and it doesn't have to be just for living things. All that needs to happen is you have something that has a concentration of something in it separated by what they call a semi-permeable membrane. And so that's an SPM right here. And then on the outside, you have a different concentration of that same liquid. Okay? And the solvent will flow from the lower concentration to the higher concentration to try to even out the concentrations. In a perfect world, osmosis will make this the same as this. A lot of things can happen in between there, whatever, but okay, osmotic pressure, then, if you're flowing into something or maybe flowing out of something, whatever, that flow causes a pressure to build up, and we can measure that pressure. And that can give us some interesting information. Now, this formula, the formula for osmotic pressure, is very related to PV equals nRT. And so here's a capital letter pi, Greek letter pi, which is osmotic pressure, not just pressure, but osmotic pressure. And C is concentration. Concentration in terms of molarity. Okay, this is an interesting one because we use molarity for osmotic pressure and not molality. And so remember, molarity is the number of moles over volume. So really, P equals N over V times RT. And so you have P equals concentration times RT. So in this case, it's just pi equals CRT. So yeah, so it's all related to the gas laws, or it's not, it takes the form of gas laws. Okay, so here's your sample problem. Okay, so we have a solution that contains phenylalanine. Now, you may not know what phenylalanine is, but it doesn't matter. If you want to know, it's I keep wanting to say peptide, but it's a amino acid, okay, and it's one of the 20 or so that, if you're biology, you need to know. But it contains 3% phenylalanine by mass. Okay, so it says the phenylalanine is not ionic, nor is it volatile. So find the osmotic pressure of the solution at 25 degrees C. So pi equals CRT. Okay. Well, we're going to have to do something to find C. So the C is going to be related to that 3% number. Okay. The R is the ideal gas constant, 0.0821. And then the T is the temperature, which is 25 degrees Celsius, which when we convert, remember we always have to convert first, then calculate, that's equal to 298 Kelvin. But let's try to figure out this C thing, okay? And I guess that, you know, I'm not purposely throwing these hard problems here, but I need to expose you to these problems that have like alternative ways. Sometimes I just can't give you the number and figure it out. So let's try to, let me see if I can show you how to figure out the molarity just given a percent. So the assumption is that when a solution is 3% by mass, how many times am I going to say 3% by mass? Anyways, when a solution is 3% by mass, that means that it's 3 grams of, I'm going to abbreviate this, phenylalanine, PA, and then the rest of it is going to be water, and that's 97 grams of H2O. Once we have that, that allows us to calculate the concentration. And remember, this is osmotic pressure, so we need the molarity. So concentration, so this is molarity equal, capital M molarity equals 3 grams. So we need to go 3 grams of phenylalanine equal, or X line, because we're converting. Then we're going to put grams, moles. So 1 mole of phenylalanine, and I'm going to bring up my calculator here. The molar mass of phenylalanine is, let's see, so for carbon, there's 9 times 12, plus hydrogen, 11 times 1, plus for nitrogen, 1 times 14, and for oxygen, plus 2 times 16. And so the molar mass of phenylalanine is somewhere around 165. So now we're going to go 3 divided by 165, and that gives us a moles of phenylalanine is 0.0182. So moles, 0.0182 moles of phenylalanine over liters of solution. Now we're in grams. The assumption always with water is that, unless otherwise stated, is that water will always be 1 gram of water will always equal 1 milliliter of water. So if that's the case, that means we have 97 milliliters, which is equal to 0.097 liters. So we take that and divide that by 0.097, and we get a concentration of 0.187 molar phenylalanine. Now it's just a matter of plugging and chugging, and I'll do this in red because it's getting a little busy around here. So it's going to be 0.187 times 0.0821, the universal Cas constant, times the temperature, 298. So we're going to get so we do the molarity times 0.0821 times 298, and we get an osmotic pressure equal to 4.59. And the units on that guy, let me just double check, are going to be atmospheres. Okay. And that is a big pressure. Okay. So that is an explanation of what osmotic pressure is and how we calculate it. So have a great day.